Hey guys, air pollution and its control is an emerging topic in environmental engineering. Nowadays, we see many questions from air pollution and its control in various examinations. Now we shall see one by one the question which are all can be expected. Now let's start with the first question. So first question deals with the types of pollutants. So which of the following are primary air pollutants? Option A, SO2. Option B, suspended particulate matter. Option C, ozone. Option D, PAN, that is peroxyacetyl nitrate. So which of the following options are primary air pollutants? There can be more than one options are correct based on primary air pollutants. So here option A and B are correct. SO2 and suspended particulate matter are the primary air pollutants among these four options. Now we shall see the types of air pollutants and some examples. So what is the primary pollutant? Primary pollutants means natural hazardous events like dust storms, volcanoes, or from human activities like burning of wood, coal, oil in homes, etc. So among these, some pollutant gases will be exhausted. So that will be called as primary pollutant. And primary pollutant may have oxides of sulfur, oxides of carbon, oxides of nitrogen, and it can also have particulate matter, that is SPM, suspended particulate matter, uh, traces of radioactive compounds, traces of halogen compounds, and some less important ones like hydrogen sulfide, hydrogen fluoride. So these are the primary pollutants. When these primary pollutants combine or react with one another, then another compound will be formed that will be called as secondary pollutants. Some examples we shall see here. One is sulfuric acid, formaldehydes, ozone, photochemical smog, peroxyacetyl nitrate. So these are some examples of secondary pollutants. Ozone and PAN, that is peroxyacetyl nitrate, are the most significant components in photochemical smog. So now we have seen what are the primary pollutants and like examples like oxides of sulfur, carbon, nitrogen, and SPM. And in case of secondary pollutants, sulfuric acid, formaldehydes, ozone, photochemical smog, and peroxyacetyl nitrate. Now let's move on to second question. Second question is, acid rain has pH value. What is the pH value or the range or the pH value of acid rain lies like it will be greater than 6, or it will be less than 6.5, or it will be greater than 4, or it will be less than 5.6. Which is the correct range of pH value that acid rain contains? Correct option is option D, less than 5.6. That is, the pH value of acid rain shall be less than 5.6, or we can say like that, a rain which has a pH of 5.6 or less than 5.6, that rain can be called as acid rain. Acid rain occurs in troposphere region. So what are the layers of atmosphere? We shall see now. So first is troposphere. It rises from 0th to 11th kilometer. 0 means the surface of Earth, up to 11 kilometer altitude. That layer will be called as troposphere, and the temperature gradient will be 15 to minus 56 degrees Celsius. And the next layer is stratosphere, 11 to 50 kilometer. Temperature gradient will be minus 56 to minus 2 degrees Celsius. And next layer of atmosphere is the mesosphere, 50 to 85 kilometer, minus 2 to minus 92 degrees Celsius is the temperature variance. And the outermost like thermosphere, and after that exosphere will be there. But these four are the major layers of atmosphere. Thermosphere will be in 85 to 500 kilometer above mesosphere, and temperature varies like minus 92 to 1200 degrees Celsius. So among these layers of atmosphere, acid rain occurs in troposphere. Why? Because acid deposition results when gaseous emissions of SOx and NOx, that is oxides of sulfur and oxides of nitrogen, interact with water vapor and sunlight, thereby converted into sulfuric acid and nitric acid. So These two are the major acidic components that will be causing acid rain. So here in this illustration you can clearly see gases carried by wind, and that gas will be dissolved in rainwater to form acid rain. So acid rain contains these two, sulfuric acid and nitric acid, as major acidic components. So this is about the acid rain. Now we shall see something about greenhouse gases. So before moving to greenhouse gases, first we shall understand what is greenhouse. A greenhouse is a construction of transparent walls and roof in cold countries to provide adequate heat to soil and plants. In cold countries like America, or in whichever the weather is not tropical, they will construct transparent walls and roof to provide adequate heat to soil and plants, so that those plants will grow like a tropical region. The solar heat or the energy penetrates the greenhouse because it is made up of transparent walls. It penetrates the greenhouse but is prevented from escaping. Actually, what happens is, for example, say this box is a transparent wall. Transparent. This box is made up of transparent walls or roof. Now sunlight is occurring here. The heat of the sunlight will be trapped here. Heat of the sunlight will be trapped here within the greenhouse, we can say. So keeping this inside of the box will be warm, so that plants and soil will get nourishment. A similar process keeping the atmosphere warm is therefore we call as greenhouse effect. So this consider this as the earth and this as the atmosphere, and the heat trapped by here is called as, is similar to or is analogous to greenhouse effect. So that's why we are calling it as greenhouse effect. So due to the presence of greenhouse gases like CO2, methane, nitrous oxide, chlorofluorocarbons, the heat remains within the atmosphere and does not escape out. So heat is remaining here. It does not escape out. So that's why global warming happens. So therefore, the greenhouse gases act like a thermal blanket surrounding the earth. So this is the reason why global warming is happening. There are four major greenhouse gases, that is carbon dioxide contributing 57%, methane contributing 12%, nitrous oxide 6%, and chlorofluorocarbons. Methane is 25 times more powerful than carbon dioxide. That means methane will be 25 times more trapping the heat when comparing to carbon dioxide. Similarly, in case of nitrous oxide, that is N2O, the heat absorbing capacity of nitrous oxide is about 230 times more than that of carbon dioxide. And in case of CFC, 15,000 times absorbing capacity. Heat absorbing capacity of chlorofluorocarbon is around 15 times, that is, sorry, 15,000 times, 15k times that of carbon dioxide, trapping the heat. So chlorofluorocarbon is somewhat dangerous greenhouse gases that has to be avoided, or we should not avoid that chlorofluorocarbon. So these are the greenhouse gases uh, which is trapping the heat as a thermal blanket around the earth, so that global warming happens. So due to this global warming, global average temperature may increase by 1.5 to 2 degrees Celsius by 2050 if we are not curbing the activities like industrial activities or anything. Then global average temperature may increase by 1.5 to 2 degrees Celsius. So, because of this, icebergs, ice lands will get melted. There will be a rise in seawater level. There will be flooding occurring in the land areas. So many consequences will be happening when global average temperature may increase just by 1.5 to 2 degrees Celsius. It will be forecasted by 2050 uh, if there is no curbs for industrial activities as of now. So now we shall move on to third question. Third question is, convert 120 milligram per meter cube of SO2 sulfur dioxide concentration into ppm. So we have to convert here milligram per meter cube units into parts per million at 20 degrees Celsius. So this formula or this for problem will be based on a gas law. We have to apply gas law formula here, and we should know what is ppm, what is milligram per meter cube, and what about the temperature variance. Accordingly we have to do the calculation. Option C 45 is ppm is the correct one. Now we shall see the calculation part. All gas at STP. What is STP? Standard temperature and pressure condition. That is, standard temperature means at 0 degree Celsius. At the standard pressure means equivalent to atmospheric pressure. So that is the standard temperature and pressure conditions. So all gas at STP occupies 22.4 liter per mole. This is a basic thing we have to remember. All gas at STP occupies 22.4 liter per mole, and this equation is the gas law. Like we have studied, like PV is equal to nRT. So nr is taken as constant, so PV is directly proportional to T. So that is why P1 V1 by T1 equal to P2 V2 by T2. This is the basic gas law we have to follow here, so that we can find the other volume. V2 is equal to V1 into, we are converting we are converting the temperature into degree Celsius, so that's why 273 plus uh, T in degree Celsius divided by 273. 273 means 0 degree Celsius. 273 Kelvin actually. Kelvin is the absolute temperature or the SI unit of temperature, but we are calculating in degree Celsius because the question they have given us 20 degrees Celsius. So that is why 273 plus T divided by 273. This is the basic idea behind a ppm. That is, 1 ppm of SO2 means 1 meter cube of SO2 in a 1 million meter cube of air. ppm means parts per million. So parts per million means how many parts in a million of sample of air. So in a million meter cube of sample of air, 1 meter cube of SO2 will be there. So that is the basic meaning behind 1 ppm of SO2. So 1 ppm of SO2 means 1 meter cube of sulfur dioxide per 1 million meter cube of air, or we can say 10 power 6 meter cube of air. This is the basic idea behind ppm. ppm is not equal to milligram per liter, as we have seen in the water. In water only it will be satisfied, in other conditions it cannot be satisfied. 1 ppm means 1 meter cube of that substance per million meter cube of the sample. Here we have taken air as the sample, so that is why 10 power 6 meter cube of air. The molecular weight of SO2 is 64 gram. So 64 gram of SO2 occupies V2 liters at T degree Celsius. So that means 1 milligram per meter. So here gram has to be converted into milligram, and we are calculating per meter cube. So that is why volume of volume at T degree Celsius in liter per mole. So that is why divided by molecular weight in ppm, parts per million. So let's substitute the values. We have to convert 120 milligram per meter cube of SO2 equal to 120 here into volume. What is the volume we have found? V2 is equal to V1 into 273 plus T by 273. What is V1? 22.4 liter per mole into 273 plus 20 degrees Celsius in the question they have given, divided by 273, divided by what is the molecular weight of this substance. Here the substance is sulfur dioxide, so 64. So it will give the answer as 45 ppm. So what are the concepts here? One is all gas at STP occupies 22.4 liter per mole. This is one concept. And next is the gas law concept. And the next is the ppm concept. What is a ppm? So three concepts together we have to know, so that we can get this formula, or we can get this idea to get what is 1 milligram per meter cube, and that will be converted into ppm. This is the basic idea behind this simple problem. It looks simple, but yeah, there are three concepts behind it. Now let's move on to fourth question. Two electrostatic precipitators are in series. The fractional efficiencies of the upstream and downstream electrostatic precipitators for size D are 80% and 65% respectively. What is the overall efficiency? They have given that two electrostatic precipitators which are connected as series. So first one has the efficiency of 80% and the next one has the efficiency of 65. Together, what is the overall efficiency they have asked? So how to find that? Let's see. Option C, 93%. It's a simple one. So we know two efficiencies, eta 1 and eta 2. So first, all the gaseous components, or we can say pollutant gaseous components, will be passing through the first electrostatic precipitator. 80% efficiency means among 100 parts of the gaseous pollutants, 80 parts will be removed, 20 parts of the particulate will not be removed. That 20% of particles or particulate will be moved on to second ESP. That ESP has an efficiency of 65%. So that's why 65% of 20 gives 13% will be removed. So how many will be removed? First we have removed 80, next we have removed 13. So that's why overall efficiency is just 18 plus 13, 93%. So this is a simple and basic formula regarding electrostatic precipitator, and we shall see some more other points regarding ESP. ESP will be used when particles to be removed, size of the particles to be removed will be more than 1 microns or 1 micrometer, and the efficiency of ESP ranging from 95 to 99%. In general, efficiency will be somewhat higher when compared to other pollutant controlling devices. Here the principle followed is ionization. This is the basic and important points to be noted in ESP. Now we shall see more about other control devices. So first is gravitational settling chamber. So this is the gravitational settling chamber. Here you can see flue gas or dirty gas will be in, and dust hoppers will be like that. Here dust components will be settling or removing, we can say, and clean gas will be getting out. This gravitational settling chamber will be used when the size of particle to be removed is more than 50 microns. That is, it cannot remove particle size less than 50 microns. That is the idea. And the efficiency is very low, like less than 50% efficiency for gravitational settling chamber. And the principle followed here is Stokes law. If you want to know what is Stokes law, you can refer this suggested video of fluid mechanics. And Stokes law will be used in other like wastewater engineering, also water supply engineering also. This is a Stokes law has to be followed here as the principle of gravitational settling chamber. And next device is the centrifugal collectors. So this is the centrifugal collectors. This will be used when particle size to be removed is ranges from 5 to 25 microns. When the particle size to be removed ranges from 5 to 25 microns, we can use centrifugal collectors, and this has efficiency of around 50 to 90%. And the principle followed here is centrifugal force. This is the centrifugal force will be applied so that the particles of size 5 to 25 microns will be collected over here, or we can say removed, and the cleaner air will be cleaner air is the output. And next is the scrubbers. In scrubbers we have wet scrubbers, dry scrubbers, spray tower, venturi scrubbers. When the particle size to be removed is more than 10 microns, we can use wet scrubbers. When the particle size to be removed is more than 2.5 microns, we can use spray tower. When it is more than 0.5 microns, we can use venturi scrubbers. Actually, in particulate matter, we have 2.5 and 10. That is PM 2.5 and PM 10. What that means is particulate matter having size 2.5 or lesser. PM 10 means particulate matter having size of that particulate matter as 10 micron or lesser. So that is the PM 2.5 and PM 10. So when 10 micron, more than 10 micron, we can use wet scrubber. And the scrubbers have the efficiency around 80% to 99%. So in the efficiency wise, we can say gravitational settling chamber has the lowest efficiency, and ESP, electrostatic precipitators, has the highest efficiency, and followed by scrubbers. Here the principle followed is flue gas having particulate matter mixes up with water droplets. Here you can see in the diagram. Here some water droplets will be sprinkled out. That will be mixed with PM. Particulate matter mixes up with water droplets and settling will be happening. That is, we are removing the particulate matter, and the output is the cleaner air. So this is the major control devices we have studied, like ESPs, what is the particulate matter size, efficiency, and what is the principle followed, and followed by gravitational setting chamber, and we have seen the scrubbers, centrifugal cyclone. These are the major things regarding device to control air pollutants. Apart from these device to control air pollutant, there is fabric filter. So this fabric filter will be used when the size of the particulate matter to be removed is more than 1 microns, and fabric filter has the highest efficiency around 99%. And in this fabric filter system, flue gas is allowed to pass through a woven or filtered fabric, which filters out the PM particulate matter and allows the gas to pass. So smaller particles are retained on the fabric initially through interception, and later on, when a dust mat is formed, the fabric starts collecting particles more efficiently. So idea behind is the size of the particle more than the fabric material will be retained, less than the fabric material will be passed. So that is the idea behind fabric filters. Now we shall move on to fifth question. The catalyst in catalytic combustion process for removing oxides of nitrogen is option A vanadium pentoxide, option B platinum metals, option C activated alumina, option D palladium. So what is that catalyst in catalytic combustion process for removing NOx, or we can say oxides of nitrogen? So for removing oxides of nitrogen, we are using platinum metals as the catalyst in catalytic combustion process. Now we shall see what are the other catalysts with respect to which we have to remove the pollutants. In case we have to remove SO2, sulfur dioxide, we have to use vanadium pentoxide as a catalyst, and this will be used at high temperature. And for NOx, platinum metals, that is we have seen in this question, and hydrocarbons, activated alumina will be used as a catalyst in catalytic combustion process. So here the burner will be there, and the catalyst will be presenting here, and raw gas will be poured here, and because of the catalyst, like for example, the raw gas contains more amounts of SO2 and we have to remove that, then the catalyst will be vanadium pentoxide. So catalyst will trap the SO2 substance and output the cleaner air. So similarly, HCC, that is hydrocarbons, we have to use activated alumina. To oxidize carbon monoxide and carbon dioxide, that is oxides of carbon, we have to use palladium 2 and copper 2. These are the catalyst substances will be used to remove SO2, NOx, HCCs, and CO and CO2. Now we shall move on to sixth question. From sixth question onwards, we will see the lapse rate, wind movement, and plume behavior. So let's start with the sixth, like adiabatic lapse rate varies between option A 9.8 degrees Celsius per kilometer and 6 degrees Celsius per kilometer. Option B 10 and 15. Option C 6.8 and 7.4. Option D 12 and 19. Adiabatic lapse rate varies between uh, which degree Celsius per kilometer? Option A 9.8 degrees Celsius per kilometer and 6 degrees Celsius per kilometer. Within this range, adiabatic lapse rate will be there. And what is basically a lapse rate? Lapse rate is nothing but in troposphere, that is 0 to 11 kilometer above the Earth's surface, that is the first layer of atmosphere from the Earth's surface, the temperature of the ambient air, or we can say environmental air, usually decrease with an increase in altitude. So on increasing the altitude from the or above the Earth's surface, there will be decrease in temperature. So temperature gradient will be like minus the temperature gradient. So that is the basic lapse rate definition. And we have two things here, ELR and ALR. What is ELR? ELR means environmental lapse rate, or we can say ambient lapse rate, or we can say prevailing lapse rate. The temperature gradient of ambient air which the rising balloon measures is called the ambient lapse rate, or we can say prevailing lapse rate. Actually, the basic idea behind this rising balloon is the ELR can be determined by sending up a balloon which is equipped with a thermometer. The balloon moves through the air, not with it, and the temperature gradient of ambient air which the rising balloon measures is called the ambient lapse rate or prevailing lapse rate. And next we have adiabatic lapse rate. Here we have dry adiabatic lapse rate and wet adiabatic lapse rate. Dry adiabatic has the gradient as 9.8 degrees Celsius per kilometer and wet as 6 degrees Celsius per kilometer. That's why adiabatic lapse rate will be varying between 9.8 and 6 degrees Celsius per kilometer. What actually is the adiabatic lapse rate is we are calculating mathematically this rate of decrease of temperature with height. Like when a parcel of air which is hotter and lighter than the ambient air or the surrounding air is released, when a parcel of air is released, then naturally it tends to rise up until of course it reaches to a level at which its own temperature and density becomes equal to that of the surrounding. So this is based on the law of conservation of energy and also the gas law. So therefore, we are calculating like a 9.8 degrees Celsius per kilometer mathematically as the adiabatic lapse rate. This is the concept behind ALR. And we have two things, super adiabatic lapse rate and subadiabatic lapse rate. We call super adiabatic lapse rate when the ambient lapse rate or environmental lapse rate is greater than ALR. When environmental lapse rate is less than ALR, then we call it as sub-adiabatic lapse rate. And there is another thing called inversion. Actually, what is lapse rate? Decrease of temperature with increase in altitude. When there is increase in temperature with increase in altitude, we call that as inversion. That is nothing but negative lapse rate. Temperature increases with altitude. So there are two types of inversions. One is radiation and another one is subsidence. In some cases, radiation and subsidence happens together, like combined action of negative lapse rate. Radiation inversion means it is a phenomenon occurring from the unequal cooling rates of the earth and the air above the earth. So there will be unequal cooling rates for the earth surface and the air above the earth. So that is why radiation inversion will be happening. So we can say like earth cools rapidly and more quickly than the air above it. Then naturally the temperature in the environment will be less at the earth and will increase above it, so causing negative lapse rate. And we can say it is the condition as inversion condition. So this inversion condition will help in rising the formation of fog, so it will contribute smog also. So that's why pollution will be trapped in the atmosphere and dispersion won't happen. So and this can also be called as ground surface inversion because it is happening near the ground surface. And next is the subsidence inversion. This is usually associated with the high pressure system and is caused by the characteristic sinking and subsiding motion of air in a high pressure area. Actually, this subsidence can be analogous to anticyclone. So anticyclone means what? High pressure regions caused by uh, like a characteristic sinking or subsiding motion of air in a high pressure area. And this inversion layer may happen around 1600 meter from the ground surface. So that's why actually radiation happens in the ground surface. That's why radiation will be called as ground surface inversion. But the subsidence happens at around 1.6 kilometer above the earth surface, and it can also be called as mechanical inversion. And in sometimes there can be happening a combination effect of radiation and subsidence that will be called as double inversion. Now we shall see the graph here, altitude versus temperature. So this straight line is called as the isothermal, that is temperature is constant throughout the altitude, that is the isothermal condition. In the left side of isothermal condition, we shall see now. This is the ALR line. We know already the ALR line. Here ELR line is there. What that means? ELR is greater than ALR because uh, on increasing altitude there is sudden decrease in temperature when compared to ALR. So that's why ELR is greater than ALR and the environment is highly unstable. Unstable means there will be dispersion of pollutant air, so that there is no trapping of pollutant air at that atmosphere. And here you can see ELR is somewhat lower than ALR because ELR, like for example say for example say here at this altitude ALR is here, like a temperature is very less, but at the same altitude here ELR is there, so temperature is what? Very higher than temperature at ALR. So that's why ELR is greater than ALR in this diagram. So ELR is less than ALR. So that means the environment is stable. Environment is somewhat stable. Dispersion will not happen in this kind of environment. And and ELR after the isothermal, or in the right side of isothermal condition, the atmosphere is highly stable. Highly stable means there will be no opportunity for the air pollutant to disperse. So this inversion condition is the highly stable condition, which is not which is not advisable. So inversion is the worst condition to disperse the air pollutants. Now we shall move on to 7th question. Wind speed measured by anemometer varying with the height for an average normal value is given by. So what is the relation between wind speed and height? Height is given by Z, wind speed is denoted by U and U naught. U naught means wind speed at Z naught. U means wind speed at Z. So what is that relation for an average normal value? Option A, U is equal to U naught into Z by Z naught power K, where K is equal to 1 by 7. This is the average normal value case. And we have another two cases. In case of large lapse rates, K will be 1 by 9. In case of marked inversions, K shall be 1 by 3. Actually, 1 by 7 is the average normal value, and we can also call it as 7th power law. This is the basic wind speed calculation with respect to height. U by U naught equal to Z by Z naught power K. Actually, U naught means wind velocity at the 0th level, or the datum, or the or at the surface of the earth, and Z is the height above the surface, which we have to calculate. or above the datum, we can say like that. So u equal to u naught into z by z naught power k, and k is equal to 1 by 7 for average normal value. Now we shall see more about wind and its relations for air pollution. Wind speed and pollutant concentration are inversely proportional to each other. That means whenever the wind speed is very high, then pollutant concentration will be low. Coriolis force tends to deflect the air currents out of the expected patterns. So Coriolis force, which will be in an atmosphere, that tends to deflect the air currents. Actually, when air current will be like this, but this Coriolis effect will deflect the air current to somewhere else. So that's why deflection of air current happens. The reason is the Coriolis force due to the rotation of air. That's why. And the next point is quicker heating and cooling of earth causes air pollution problems. Quick heating and cooling of earth causes air pollution problems, as we can see in the coastal regions. In the coastal regions, there will be some air pollution problems because of sea breeze and land breeze that will cause the quicker heating and cooling of earth. And next point is the gustiness. Gustiness means strong wind intensity or strong wind velocity, like that. So gustiness of surface wind determines the extent to which pollutants are mixed and diluted with the ambient air. Whenever there is gustiness of the surface winds, then the pollutants are mixed and diluted with the ambient air. So gustiness level determines the mixing and dilution with the ambient air. These are the points regarding wind speed and wind regarding air pollutant dispersion. Now we shall move on to next one. Most favorable plume behavior is. This concept is the most important concept in air pollution. This plume behavior can be expected in many examinations. Here we have to find, or we have to know, what is the most favorable plume behavior. Option A looping, option B lofting, option C neutral, option D fumigating. So what is the most favorable plume behavior for the dispersion of air pollutants? Option B lofting plume is the most favorable plume behavior condition, and we shall see one by one the uh, various plume behavior. So first we shall see the looping. Looping means here in the diagram itself you can see there will be loops of gaseous pollutants arising from the chimney of a industry or factory. Here you can see super adiabatic lapse rate is prevailing. Super adiabatic lapse rate. And next is the coning. In the diagram itself you can see there will be cone like formation of the gaseous substance from the factory or industry, and here subadiabatic conditions will be prevailing. And next is the fanning. This is a extreme inversion condition. What is inversion? We have seen increase in temperature with increase in altitude, so that is the negative lapse rate. That is the inversion, which will be most unfavorable. And we can say like atmosphere is most stable. The stable atmosphere is not favorable to disperse the air pollutants. So fanning condition is the uh, fanning condition means there is inversion condition. Next is the lofting. Lofting means there will be inversion above the atmosphere. So that means what? There is a strong super adiabatic lapse rate above surface inversion. So then that plume will be said to be lofting. That is, ELR is greater than ALR here. ELR is greater than ALR above the surface. This is the surface phenomena, like we can say. Below it, which inversion happens. So that's why mixing will be above the chimney. So that is why no gaseous pollutants will be there in the city. So that is why lofting is the most favorable plume behavior. You can see in this diagram below here. there is inversion. Above this line, ELR is greater than ALR. That is strong super adiabatic lapse rate is prevailing above the surface inversion. So this is the surface inversion. So above which ELR is greater than ALR. That is why lofting is most favorable plume behavior, because no gaseous pollutants will be trapped inside the city. And next we shall see fumigation. Fumigation is the inversion of lofting. What is lofting? We have seen above the surface inversion there will be strong super adiabatic lapse rate. But here ulta, that is below the surface inversion there will be super adiabatic lapse rate prevailing. Above the surface inversion, or we can say above this line, there will be inversion. So then dispersion may not dispersion will not happen here. Dispersion only happen here, that is at in the surface of the city. Then the city will be getting polluted. So lofting and fumigation are inversely related. Lofting means above the surface inversion there will be super adiabatic lapse rate, and the inverse is the fumigation. And trapping is nothing but all the gases will be trapped inside the surface like this. Actually this diagram is not correct. Trapping means all gases will be trapped like this, trapped between two surfaces. Below this line there will be surface inversion, above this line there will be inversion, and here only there will be super adiabatic lapse rate. So that is why it is called as trapping. Gases will be trapped between two layers, two inversion layers. So among these plume behavior conditions, lofting is the best one, and fumigation is the worst one. So that is why it is both are inversely related. Lofting best one, fumigating worst one. Here you can see neutral plume means ELR equal to ALR, that we know. When uh, this neutral plume, that is what neutral plume is. For example, say this is a chimney. Gaseous pollutant will be moving like this in the straight way. So this is the neutral plume, that is ELR equal to ALR, and it will be tend to cone like appearance when wind velocity is greater than 32 km per hour. So we have studied looping, coning, fanning as inversion, and lofting. Now we shall move on to next one. This question is to find the height of the chimney. So they have given some data. A factory uses 1.5 million liters of fuel oil per month, and the exhaust gases contain particulate matter of 4 tons, sulfur dioxide of 20 tons, oxides of nitrogenous 5 tons per million liter per year. Per million liter of fuel per year, there will be this much exhaust gases. So according to the air pollutants or gaseous pollutants arising from this industry, we have to find the safe height of chimney accordingly, so that there will be no gases trapped inside the city. So option A 43.5, option B 63, option C 100, option D 52 meter. So what is the chimney height required on the basis of gaseous pollutants given as like particulate matter, SO2 and oxides of nitrogen? Here the answer is option D 52 meter. We have two formulas according to which we have to find the height of the chimney. On the basis of particulate matter, we have H is equal to 74 into Qp per 0.27. Here particulate matter quantity should be in tons per hour, because this is empirical formula, H in meters, and Qp in tons per hour. So first we shall calculate that. They have given PM quantity as 4 tons. So 4 into 1.5 into 12. Why? Per million liter. So that's why how many million liters of fuel oil? 1.5 per year. So per month 1.5 means into 12 for a year. So 4 into 1.5 into 12. So that will give 72 tons per year. Here we have to substitute in tons per hour quantity. So we are calculating 72 by 300 into 24 by assuming 300 working days of this factory or industry. So 72 by 300 into 24, that gives 0.01 tons per hour. So this value to be substituted here. So we get the answer as 21.34 meter. And on the basis of SO2, H is equal to 14 into Qs power 1 by 3, or we can say 14 cube root of Qs. Here Qs, that is quantity of sulfur dioxide, should be in kg per hour, and sulfur dioxide is around 20 tons. 20 into 1.5 into 12, as same way we have to calculate 360 tons per year. Assuming 300 working days, 360 by 300 into 24, that will give 0.05 tons per hour is the answer. But we have to calculate in kilogram per hour, so that's why into 1050 kilogram per hour. So that's substitute here, so that we can get the answer as 51.58. And next they have given the oxides of nitrogen. This oxides of nitrogen, carbon, hydrocarbons, fluorides, these are some trace quantities, and particulate matter and sulfur dioxide only contributes more uh, to the gaseous pollutants when comparing with oxides of nitrogen, hydrocarbons, and water vapors, others. So that's why we are calculating only on the basis of PM and SO2. So we have two answers, 21.34 and 51.5. Higher value has to be taken as the chimney height. So that's why answer is 52 meter. Now we shall move on to last question. So this question is also based on height of chimney or height of stack. Here we have to determine the effective height of stack with the following data. So they have given some one set of data according to which we have to find the effective height of stack. Option A 180 meter, option B 176.36 meter, option C 188.92 meter, option D 150 meter. So we have to use Holland's equation or Holland's formula here to determine the effective height of stack. Now we shall see the answer or the calculation part. First we have to denote the given data like this. Small h is 180 meter, that is physical stack height, and capital D is 0.95 meter, that is stack inner diameter. Actually this physical stack 180 meter height will be got by the previous formula, like we have seen in the ninth question. Physical stack height based on SO2 based on particulate matter. So by using that empirical formula we can get the physical stack height, and we are denoting here as small h, and a capital D 0.95 meter, and pressure 1000 millibars, and small u is nothing but wind velocity 2.75 meter per second, and the stack gas velocity V suffix s is equal to 11.12 meter per second. And next is the what TA is actual temperature, that is absolute temperature, actually not actual, absolute temperature 293 Kelvin, or we can say 0 degrees Celsius. Here we have to substitute only Kelvin, so that's why 293 Kelvin, actually 273 Kelvin actually. 273 is the absolute, but here the temperature is 20 degrees Celsius, so that's why 273 plus 20 gives 293 Kelvin. And TS is the stack gas temperature, so 160 degrees Celsius plus 273 gives 433 Kelvin. This is the Holland's equation. Del H means, what is actually the del H? Consider this as a chimney. This is how gas will be rising. This is the physical height, that is small h, and this is the del H value. This del H we are calculating using Holland's equation. So H plus del H is the effective height of stack. So del H is given by Vs into D divided by U into 1.5 plus 2.68 into 10 power minus 3 PD into Ts minus Ta by Ts. So just substitute all the values in this units only. H in meters, D in meters, pressure in millibars. pressure in millibars, U in meter per second, Vs in meter per second, and temperature in Kelvin. In this unit only we have to substitute here so that we can get the answer for del H, that is this one. So del H is got as 8.92 meter here. Original physical stack height is 180, so 180 plus 8.92. So option C, 188.92 meter is the correct answer. Now we are at the end of this video. We have learned the expected questions from air pollution and control. We can expect these type of questions in many examinations, especially on GATE exam, ESE, and many other uh, public service commission examinations. Thank you for watching this video. Please stay tuned. Please stay tuned for upcoming videos also. And please subscribe the channel and also watch the suggested videos here. Thank you so much.